Greetings and welcome. In this video session, we will study about the Bootstrap cooling system. The difference between Bootstrap cooling system and main cooling system, that first of all we will see. Basically, for higher speed, Bootstrap air cooling system in a aircraft refrigeration system is used. In a simple air cooling system, we have seen that there is one compressor and one heat exchanger after the ramming process. Here we have two compressors. So first compressor is called as main or primary compressor, and second compressor secondary compressor. Here two heat exchangers are used. So one is used as a air cooler, and after the turbine again heat exchanger is placed. That is why it is called as after cooler. Now overall effect or overall advantage of this system is what? It provides additional cooling capacity. Now we will see its schematic diagram, and then for the analysis purpose we need TS diagram. So let us see construction diagram schematic of the Bootstrap system. Here we have, this is as usual 1 to 2, that is a ramming process. This takes place in a diffuser section. After ramming 2 to 3 is a main compressor, main compression process. 3 to 4 at the end of compressor, then it passes through that air passes through the air cooler, that is heat exchanger. First primary heat exchanger, we call it as air cooler. This air is cooled by using the air. That air is bypassed from the starting before the ramming. This air at point 1, that is a starting air, this bypass air is utilized for the cooling purpose in both heat exchanger, here and here. So that is why it is shown by the blue color line. So this air is used for the cooling purpose. That is why here the heat transfer that is taking place from this hot line to this line, and this air carries the heat, and that is released to the atmosphere through this exit jet. So 3 to 4, this is a heat exchange process, means cooling process. Then it goes to the secondary compressor. In a secondary compressor, 4 to 5 second compression is conducted. Then further second time in after cooler, that air is cooled between process 5 to 6 by using the again this bypassed air, which is from the start of the system, that is ambient air, this is cold air. So here also this line heat transfer takes place from this cold line to this line, because this is a after compression. That is why somewhat this line goes warm, this air. So that is why heat transfer take place. Sorry, here the journey is from left to right, like this. This is a warm line, warm temperature line after compression. That is why heat transfer take place. The heat is carried from this line by this another line in after cooler, and that heat is released to the atmosphere through the exit jet. This air which is been cooled, that again is passed through the turbine. Here the expansion process take place 6 to 7, and then the air which is going to the cabin, that is point number 8, cabin. Now this is what the journey of air from the entry to cabin in the Bootstrap air cooling system. Now we will need its TS diagram for the analysis purpose. So we will have here. So now here we will see the processes, different processes. Process 1 to 2, ramming process, isentropic ramming process. In a primary compressor, this is ideal compression, and this is actual compression. 2 to 3. 3 to 4 is a cooling process in a primary heat exchanger, that is air cooler. 4 to 5, that is in second compressor, secondary compression. 4 to 5 Here 4 to 5 and 4 to 5 dash, ideal and actual. 5 to 6, again cooling of the air in second heat exchanger, that is called as after cooler. After cooler, then 6 to 7, that is expansion in a turbine, and 7 to 8, that is a journey of the air from the turbine to the cabin. So this TS diagram now we will use to write the formulas. Further process 2 to 3, that is the next part, that is compressor efficiency. By using compressor efficiency, compression operation take place between point number 2 and 3. This is the ideal process, this is the actual process. Ideal temperature rise divided by actual temperature rise. This already we have seen in a thermodynamics, also in first sessions. So accordingly, this formula will give us value of compressor exit temperature T3. Then process 4 to 5, this is a process. During this process, here we use, this is a 4 to 5 process, that is in a second compressor. So in second compressor, again ideal temperature ratio to the pressure ratio. By using this formula, we get value of T5 dash. This T5 dash we use to put in the compressor second efficiency formula. In a second, from the second formula, we find the value of T5, that is the exit temperature of the compressor. Now further, next 6 to 7 process. This is what turbine or expansion process between 0.6 and 7. So here we use this formula, temperature ratio between 6 and 7 point. From this formula, we obtain value of T7 dash exit, ideal exit turbine temperature. And by using this turbine efficiency formula, this is a formula that is temperature drop during the expansion process, ideal temperature drop, because it is smaller than the actual. So smaller divided by larger temperature drop. This is the formula. This formula gives us temperature of exit of the turbine, that is T7 actual temperature. Now here two heat exchangers we have seen in the diagram. First one is a primary heat exchanger, that is air cooler, and second one is after cooler. So for the air cooler effectiveness formula, 3 to 4, during this process temperature is increased. So this temperature at the compression, here we will see during the compression process. So 2 to 3, this is a from 2 to 3, during the compression 1, the temperature which is been raised, this heat we have to remove. So that heat is removed in this process 3 to 4. So this is a heat removal temperature difference divided by heat addition. That is what given in the effectiveness formula. T3 minus T4 divided by T3 minus T2. Similarly, effectiveness of the after cooler, heat exchanger number 2, we call it as after cooler. So this heat exchanger 5 to 6, that is a heat exchange process take place 5 to 6. This is a heat exchange process, heat removal process, air cooling process in a after cooler. So from 5 to 6 means T5 minus T6. This is a temperature difference which is taking place during the heat rejection, divided by the temperature rise due to main compressor, that is 2 to 5. So that is why the formula is here, effectiveness formula, what we use. T5 minus T6, that is the heat removal process in the heat exchanger, and T5 minus 2, that is the increase of temperature due to main compression. So in this way, these two formulae we use during the numerical, depending upon the data availability. Either the temperature is given, or heat effectiveness of the heat exchanger values are given. Next one is to find the powers. So here are two powers, two work done that already we have seen in a simple air cooling system. First is during the ramming process, 1 to 2 process, that is why formula is MCP, temperature difference T2 minus T1 in a kilowatt. In a compressor 1, compressor input, that is during process 2 to 3, so that is why formula is MCP, temperature difference T3 minus T2 in kilowatt. Net work is what? Summation of these two, that is WR plus WC1. Cooling capacity or cooling load capacity of the system, that from the diagram, if you see here, this is a process. At the end of turbine, exit of the turbine, the air which is cooled, that air is passing to the cabin. During the journey, that heat of the cabin, that is absorbed by the air. So here the load which is added to the air from the cabin, that is what MCP delta T, mass of air MA into CPA specific heat into temperature difference 8 and 7. So that is why the formula is Q dot L formula. Between 7 and 8 process, 7 to 8 the process, that is a cabin. So MCP into temperature difference T8 minus T7. This is what cooling load in kilowatt. This we convert into capacity, dividing it by 3.517 ton of refrigeration TR, that is the capacity of the system, that is calculated by dividing the value of kilowatt by 3.517, that is a factor, conversion factor. And finally, performance index, that is COP, coefficient of performance, that is ratio of cooling load, that is output, divided by net work, which is input to the system. So in this way we find the COP. So in this way we have seen today in this session Bootstrap air cooling system, its TS diagram. First of all we have seen construction diagram. After that we have seen its TS diagram. From the TS diagram we enlisted for the different processes formulas, temperature ratios and efficiencies, in case of heat exchanger effectivenesses, and at the end we put the formulae for the output and input. Output is a cooling effect and inputs are RAM work and compressor work, and then COP, that is performance index. So this was about the Bootstrap air cooling system. Construction, working and analysis of the system.